So today we're going to look at problem 13.9 from Martin high-dimensional statistic. So let's look at the problem together. So we're interested in studying a function class f and where each element is a function f in certain form, where this function gj is in G, we call it flower G. Gj is actually just like a function from R to R as defined here. And we also have an additional constraint that the G norm of the function Gj is less than or equal to 1. So that's the basic definition for the function class f at. And since we are studying, we're studying chapter 13, which is about the least square estimators. So we're interested about f hat, right? We want to estimate the true model f star. So this is a pretty standard setup where sigma is a constant and wi is a standard normal portion and variable. And so f star is a true model. It can be written in the summation j is equal to 1 to b of gj star, where gj star is a function in the flower G, right? So by the definition of least square estimators, f hat is equal to this. And in addition, the author actually gave us a pretty good hint. So let's look at the localized Gaussian complexity for each coordinate j defined in this way. Here is 2 flower G because we want to make sure it is star-shaped. Why do we want it to be star-shaped? Because we want to make sure the critical inequality, which is this, holds, right? Okay, so, and the mj to be defined in the smallest positive solution where the critical inequality to hold. Now let's look at part 1. Let's define delta n max to be equal to the maximum amount delta nj. And we want to show that for t that is larger than delta n max, we have this inequality hold with probability at least this much. So this immediately tells us or gives us an intuition about the concentration inequality, right? So you need to recall what we learned in chapter 2 of Martin high-dimensional statistics. So, and then in addition to that, we define the notation delta j hat to be the error function on each coordinate, and delta hat to be the summation of all the error functions from each coordinate, and then we call it full error function. So let's try to solve part A. So we're gonna use this expression a lot. So why don't we just give it a name as ZPJ, right? Okay. So there are a couple of main statements that I like to outline. The first one is we want to show this concentration inequality. It might be not clear why do we need that, but once you get this, the other statements follows kind of immediately with some observations. So we can split into cases, smaller than t and larger than t. And then at the end, we're going to combine those two to obtain the concentration inequality for all the cases. And right. So let's get started. So first, we want to, so recall that I mentioned that in part A, it actually gave us like an intuition about using the concentration inequality. And if you went over the proofs in chapter 13, there are quite a lot of proofs used theorem 2.26. And the expression of the theorem or the expressions that we are mentioning in the proof actually looks a lot like the expression here. So I'm going to use theorem 2.26, and that's actually the first one I tried. So in practice, for other problems, it may be not a good idea to use 2.26, but for this one, I have at least I want to try to use 2.26 at the beginning, at the very beginning, from the first try. So and luckily it works. So let's see the details. So recall theorem 2.26. It is about Lipschitz functions. So in order to use the theorem, we have to show the conditions are satisfied. So one of the conditions is, so one observation that we can recognize the expression as a function of Gaussian random variable. Then we want to show this is a Lipschitz function with certain constant, Lipschitz constant. So I did all the work here, and you can pause and read through it. Let me know if there's some questions. So I'm gonna skip the detail and let's go. Let me jump to the next step. So what I did basically is just to follow the definition of Lipschitz functions. So we have HW minus HW prime at the end is smaller or equal than sigma over square root of n times the L2 norm of the difference W minus W. Or by the just by the definition, this is a Lipschitz function with constant sigma over square root of. And therefore, the conditions of theorem 2.26 are satisfied, and therefore we can apply that and to obtain this concentration inequality on the top, which is this. So if you look at the concentration inequality, if you're familiar with the proof procedures of the theorems in chapter 13, the next step naturally is to find what this expectation is. So let's write it more explicitly. I just apply the definition of ZTJ and I obtain this, right? So I can just directly replace this in this concentration inequality and I obtain this one. And by looking at this, you see something familiar, right? That is something mentioned in the hint given by the author. So I work in a good track. So by assumption, T is larger than delta n max, and we call the definition for delta nj, where each j equals to 1 all the way to n. So therefore, we have this is smaller equal than this. I just copy down directly from the above. So I made the denominator smaller and I also made the in the localized Gaussian complexity the first parameter to be smaller. So this inequality is valid. We actually use this inequality. You actually have seen this inequality in some of the proofs in chapter 13. And continue, we have this is smaller equal than this. Now from here to here, we actually use the fact about this critical inequality. Okay, and then this and this canceled out. This and this canceled out, and therefore we got this. And then this is smaller equal than max, right? So everything follows pretty naturally. Okay. So let's see what do we have here. We have events. So at the beginning, we have this concentration inequality. Now, as I said here, since the event A implies in event B, where event B is actually this couple lines, right? Therefore, we have this inequality. And so far we are proving statement 0, which is the foundation that we needed. So we're getting closer to closer. The next step is to let U be T over 2. And let's see where that leads us to. If we replace U in this inequality, the inequality that I am drawing the line, we will see that we will obtain this inequality. Here, we didn't do anything complicated, we just replace U with T over 2. And if we simplify, we will get the next concentration inequality because T is larger than delta and max. So we obtain this, and then I use this. And then therefore we finished our first statement. I will remind you about this expression later in the proof because it's pretty important and we need to use this. So now let's consider the case that this is smaller than T. What would happen if this is smaller than T? It's actually the easier case. So this is equal to this. Recall that delta J hat is equal to, despite the definition, it is equal to the difference between Gj hat minus Gj star. And we have, so because Gj hat and Gj star, they're both in flower G, therefore their difference in the flower G. So therefore, this belongs to flower G. So we can, it must be upper bounded by the supremum over, right? It must be, here I made a mistake. This actually means I need to write Gj in Gj. So it must be upper bounded by the supremum. So we got this. And then this is just the VTJ. And then next we so here is the first the inequality, the first concentration inequality from statement 0, which is this. So this is if and only if, right? Because we just put t to the right side. And then if you look at the inequality, so this is smaller equal than this, and this is smaller equal than t squared. So it's very common probability procedure. So because one event implies another event, so the probability of that first event must be smaller equal than the second event. So therefore we have this inequality. And that proves the statement 1. And then now we need to prove statement 2, which is the case that the norm of delta J hat is larger than T. So first of all, we're going to make an important observation. We want to show the claim, right? The claim this is correct. Let's see why it is. So this is equal to this. We just here we divide by this and we multiply by this. Why do we want to do that? Because, well, after you normalize n times t, you actually have the norm as I write here is equal to t, which is smaller than t. Why do we want the norm to be smaller than t? Because then we can apply the definition of VTJ, right? So we have this expression. Notice that because in this case is larger than t, we need to times this extra terms. So we finish our claim. So that is our important observation. And this implies this concentration inequality because we explained the observation and we actually going back to this important concentration. So we notice that if we multiply delta J hat on both sides, the inequality does not change, right? So that's why we got this. That's why we got this concentration inequality. Well, technically, there's no implication, I'm sorry. So we have this, and this is just the fresh observation we made. Right now, you may don't see the immediate connection, but we'll show you. So because by the definition, by the observation, right, Let me highlight it. So this, let me change a different color. So this is smaller than this. And then meanwhile, we also have this smaller than this. So if you use the similar probability techniques, you will find like implication, right? If one is smaller than the other, then the one even smaller must be smaller than the largest one. So it's kind of like the implication and the probability inequality as we did before. So together we have this is larger than this. So together we got the last inequality. And that is exactly the statement 2. So now we almost done with part A. We just need to combine and make it looks in terms of delta hat instead of delta hat, delta J hat. Right? Okay. So if you recall, in case 1 where delta J hat is smaller than T, I can show you. So, so in this case, we have this. We have with a smaller equals than T squared. Well, of course, this is smaller equal than T squared plus T times this, right? And then again, using the implication of the probability, you will see that in this case, we actually have concentration inequality T sigma over N summation Wi delta J hat xi smaller equal than T squared plus T delta J large N equal to T squared. I think I need to type in here. Right? So, and similarly, for this case, we also have the same concentration inequality, this one. So no matter which case we are, this holds for both cases. So that is pretty good. And then I write down here, right? And then therefore we get this. And again, I need some typos here should be negative. And then now, if really the last step is to write in terms of delta hat rather than delta J hat. So we need to sum them. So notice that we have this is equal to this. Here, I just apply the definition, right? They're the same. Again, you can pause the video and check my work. And at the end, I obtain this. And again, one event implies another event. So the probability is going to be the probability of this event is going to be smaller than the probability of this event. We have seen this many times in this proof, so you should be already familiar with it. So therefore, we have this concentration inequality. And we're almost done. So in order to obtain the concentration inequality that required by the author, asked by the author, we need some observations, right? Since like we're thinking what kind of team that can let us so that we can obtain exactly the same expression as the one that the author asked us to do. So here is pretty simple. We need to replace t with t times delta n max, and together take the square root of it. And then once we do that, we can see just by simply replace t with square root t delta n max, we obtain the concentration inequality. It's exactly the same concentration inequality without a constant. The other has a constant too, but we don't have it here. But since it's a constant, it's not a big deal. So we're done. We're done with part A. That is what the author asks us to do. And now let's look at part B. I would say part B is a little bit simpler once you solve part A. So here we have additional assumption about this. And we are asked to show this inequality with high probability. Again, that reminds us about the concentration inequality, right? And another important observation that I will show at the beginning is this is actually equal to delta hat. Right. So let's jump into part B. So first of all, we're going to review a little bit the notation that we saw in the lecture. So this, so F hat is least square estimators, and is arguing this is a special, really just a special notation. The hat here means 1 over n summation I is equal to 1 to I is equal to n. Nothing special. And then this inequality is easily understood because F hat is odd mean, so of course anything else other than F hat is going to be larger than right once we plot it. So using this we can derive what is called the basic inequality. Again, if you read chapter 13, you see this a lot. This is called the basic inequality. Almost, I think, theorem 5, theorem 7, theorem 23. So all the major theorem in chapter 13 at the very beginning, the author must list the basic inequality, and you should be very familiar with that. So you can possibly even check my work. So here is the result. Let's just look at the end result, right? So at the end, we obtain this. And then what's below this is just I really want to show you that the Ln norm of this is equivalent as the Ln norm of delta hat. I'm sorry about my typo. So this is the basic inequality, and we need this. Okay. So what is this? This is the result we derived from part A. I can remind you. So this is this inequality. Before we replace t with square root t delta n max. So, and I give it name, right? And let's go back. So we have this inequality, and let's make some observations again. So again, here I missed maybe one step, which is again the implication of one event means the probability is smaller than blah blah. So because we have this inequality, and we also have this inequality, so this actually implies this this concentration inequality. I mean, I just keep observation on this concentration inequality. If you look at dt squared, recall that k is larger or equal than 1, so dt squared is going to be smaller than or equal than dkt squared. So that is there. And then for the second one, we can think it as a product, inner product of two vectors, and we can use Recursion-Schwarz inequality. So this is equal to that. And so putting everything together, about we get oh, and also replace t with delta n max. So here is a t, here is t squared, right? So we replace it with delta n max. So this is equal to, so we obtain a new updated concentration inequality. And we are almost done, so conclusion. So again, one thing that is very common in this type of proof is we consider two cases, right? So either the n norm of delta's hat is smaller or equal than this, or it is larger than this. So those are the only two possibilities. And we argue that either, no matter which case that you're thinking about, the final result holds. So therefore, the final result holds without any special cases. So that's the idea, right? We see that techniques a lot actually. So when the n norm of delta hat is smaller than square root of dk times the delta. I'm sorry about the same name. When I say delta hat, I mean this. So delta n max is this. So when in this case, we have this. This line can be applied, can be obtained directly from the line above. We just replace this with square root of dk times delta n max. And then we put the constant to the right hand side to obtain this concentration inequality. And then we're done with this case, right? That looks exactly the same as the one that we're asked to prove. And now let's look at the case that n norm of delta hat is larger than square root of dk times delta n max. So in this case, It's not hard, but it's a little bit different type of observation needed here. So again, we have this. So what I mean here is, so if you look at this part, this is equal to dk square root delta n max times dk delta n max, right? And I keep this the same, but I replace with delta hat n. And then we have an upper bound because this is larger than this. So therefore we have this concentration inequality. And then just to simply combine everything, this is 2 times this, and then clear out the constant. We have, I think I made a mistake. I think this should be 4, right? This should be 4, and this should be 16. So again, this is a constant. So in both cases, here this is a 4, here this is 16. So we can say the first constant is, it doesn't really matter. We can just say 16, or we can just say there is this constant C3 such that this concentration inequality holds. And this is exactly what the other asks us to do. So we're done. Thank you for watching, and please let me know if I have made any mistake or there's any typo. You reach out to me by emailing to me. See you next time.